So you can just say, all right, you're smart, and you can give a hint. And sometimes that's actually a very good plan. So I'm kind of joking a little bit, but in reality, hints are very useful to give hints. So you can give hints on a SQL statement. You might have a subquery or a subquery, and you can give a hint on the inner child query. You don't have to do it on the parent. So you can give hints at different points in time and tell the database what to do. Or you may know that the data distribution early on looks like something, but later on, down the road, 6 months from now or a year from now, your data is going to have a different distribution, and you can add the hint or remove the hint, while the data grows, so you can do a different kind of a plan. Maybe if one set of data in a table only grows slowly, you'll give a hint saying, do a full scan on that table rather than doing lots of queries, and then you know that once your data volume gets pretty big, you can remove the hint and let the optimizer choose a different plan. So you have a lot of options here. Yes, sir?
I have a question.
Please.
Is optimizer always follow hints? Or sometimes he,
Does it ignore?
yeah. Some database engine sometimes ignores hints.
So generally it does its best to follow the hints when you give a hint. I can't promise that it always is well behaved. Just like kids, they can be temperamental and want to do their own thing, or spouses, depending on your example. But generally, it will trust you if you give a hint. Now, sometimes you may give a hint that's impossible. So you may say, I want to do an anti-join on this type of statement, but you can't even do an anti-join, or that's not possible based on the construction of the SQL. So then it will obviously ignore your hint.
So bad hints doesn't produce an error. Optimizer simply ignore it and execute it.
Yeah, so it will use the hint. Now the hint doesn't necessarily describe the full path. The hint might say, start with this, even though I wrote the statement because maybe I dynamically generated with a from statement with table 1, table 2, table 3, I know table 2 is the smallest and I want to drive the statement with table 2. You can put the hint in just to talk about one part of how you drive your SQL statement. It's not going to describe the entire path. Usually it's a hint, it's not the whole plan. There's no way to enter the entire plan, which might have 12 steps or whatever it might be. So again, that's why it's called hint as opposed to do it, damn it, or something. But generally, what it does is it forces the optimizer to use a particular algorithm or an access path or a join order or some sort of join operation. You obviously, the other things, you can modify the SQL statement, and we'll talk about a lot of examples where we modify a SQL statement. We talked also, you can alter the infrastructure, you can add and move indexes, you can cluster your data, partition your data, possibly you can create materialized views as temporary storage for aggregated data. Let the database, in other words, let the database do all the work for you, but do it in the background asynchronously instead of waiting for a user to actually say, hey, I want that data. And then you can obviously tune the Oracle instance itself. You could pull a lot of data out and just archive it, reducing the size of your tables. You could restructure and move table spaces. So, as you build your application, maybe the default is everything's in one table space. But as your data grows, you might want to say, I'll put the indexes in one table space and have some other tables in a different table space. If you have, for example, you're doing a join with 2 different tables, you want to make sure that those 2 tables, particularly if you're on a machine that has multiple CPUs, you want to make sure that maybe the data from those 2 tables are stored in different table spaces, in other words, in different physical files in the operating system, so you can maybe access and pull the data in parallel, which you can't if they're too tightly clustered, And obviously you can just tune the Oracle instance itself, which we talked about a little bit earlier. So, things to consider when doing tuning everything, okay? I will not discuss everything. We will run out of time, you guys will. So, let's talk a little bit about different indexes. So there are 5 kinds of indexes in Oracle. The most common, which everyone sort of knows about, which is sort of the default out-of-the-box index, if you took computer science, is your standard B-tree. And a B-tree index, basically, if you have a query, it creates a tree, it tries to balance it, B stands for balance, tries to create these balanced trees where you have different nodes, the data so it moves around, and when you do a query, typically this is the most common way to access data, is going through an indexed tree. You can use concatenated index. Concatenated index is when you have multiple columns. When you're querying, you have an index with multiple columns. For example, this one you have last name and you have salary. If you have that, if I'm doing a query against salary only and not with last name, then this index is useless to me, right? Because this index is in a certain order. And you want to have that in order, and you want to define the order where you have sort of this is more restrictive and then this is less restrictive. The next kind of index, which is also very common, is a bitmap index. So you use this with data. The example I have is sort of like a car kind of network. You eventually sort of Google, the way it does searching, it actually has created its own custom indexing structure, but some of the logic and the thinking is very similar to the concept behind bitmap indexes. This is when you have lots of data with very low cardinality. This is also a set of technology that's very similar if you're doing OLAP, if you're doing warehousing, and you have a star schema. You probably want to use bitmapped indexes as well. So again, I'm searching through a database with 1 million cars, and I want to find some that are blue, some Toyotas, some from different years. And each one of them, the number of cars that are blue or black in the database, if I have 1 million cars, there are only maybe 10 or 12 colors. So that means, I'm going to probably have 1 million rows which are black, and 1 million, I'm going to have thousands that are Jaguars, and thousands that are from different years. Though the years may not be balanced, you probably have more recent cars than older cars. So if I would have used a regular B-tree index, number one, it wouldn't do me a lot of good if the index was constructed color, make, year, and I didn't care about the color. And I only asked for make and year, I would have a concatenated index, and I wouldn't be able to use it because I didn't ask for a color. So I'd end up doing a full range scan over my entire index, pulling everything. So this way, you can create a collection of bitmapped indexes on the different attributes and let the engine in parallel look for the blues and the Toyotas and the 81s and generate a subset, because your data, otherwise you'd be doing huge range scans. Or you could say, just for these 3 columns, I would have to create 6 different indexes, with a different order of columns, depending on what I'm querying. So that's the concept of a bitmap index, and it's a very powerful and useful technique. And so when you define your table, and you understand how the data works in your table, you're going to want to create these kind of indexes instead of B-tree. Your queries will go orders of magnitude faster alone. Okay, good. So there are other kinds of indexes which, again, not used very often. You have an index-only table. So in other words, if this is sort of like a lookup table, I don't have that many columns, you can actually say, well, I don't need an index and a table, because by the time I find everything in the index, I've got almost all my data already anyway, because I'm not pulling 10 columns, I'm just probably pulling 2 or 3. So why produce 2 different structures? So you can create an index-only table, which basically says, store this table as an index in like a tree structure, and I know how I'm always going to query the data. It's always going to be through, I know that for this example, I'm always going to have an employee ID and probably a name or something like that. So I'm just going to construct this table just to be an index. So when I find in the index, I walk through a B tree. I'm doing, once I have that B tree, which again is a log n type access speed, I've got the data all right there in that leaf in the index. And so I don't even have to go look up data and do any more reads. I've got it all right there. And so that's another very useful mechanism. You can use it for lookup tables. Though again, lookup tables you're probably going to read and cache in your application, but if you have large lookup tables or different things, that's an example of where you might use an index-only table. Then you have what we call FBIs, which are functional bitmap indexes. So these are actually useful when you have a SQL statement. So if I have a statement select star from customer and I'm doing some operation on the column in the database. Well, if I'm doing any operation on a column, I can't use an index. So this SQL statement would not use any index, because even if you have an index on order date, I'm doing an operation on it, so the values in the index are not this operation, but it's the whole address. So I'm going to do a scan of that table. So you can actually create an index on to-char order date, just the month, if I want to look up just the month. And so the index actually doesn't contain the order date, but it actually contains, these 2-character strings. And so that's the index. So if I have this query, I can now look at it and actually use an actual index to do the lookup. Though, as it turns out, there are only 12 values. You're going to be doing a range scan anyway, probably. And again, the same thing here. I could do it for any particular criteria. I could actually create the index on those values, and those are the actual leaves in the index itself. I could use an in-memory table. So in other words, I could basically say this table just sits in memory. If it's something that I have to query, I can't cache in the application, I'm actually going to basically, anytime I do a read on this table or any data in the table, I want the database to save this stuff in memory. So you have to make sure you allocate enough in your SGA to store this, but that's fine. The database will say, hey, that's cool. And it'll keep, so once it reads any blocks or any data, that data is in memory, and it doesn't have to again go to the file system to pull the data that it needs. And then you've got other things, I mean, clustered indexes, partition indexes. So if you know for your data that for a particular key, there's lots of records and you're going to pull it all together. So maybe you can cluster your data. And now this is not exactly how Facebook or social networking works, but if you have all the information associated with you clustered, that way when you open your page, all the data you're physically reading, the machine can just basically say, all right, this set of blocks is all related to a particular key. The key is Leo, and therefore I know that if I'm reading anything whose index value is Leo, I don't have to read some data here, and some 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 over there, and some under Nick, or over there. It will store all the data related to this index key, the key Leo, actually physically together in the same blocks or in blocks that are near each other. So you can define your table with these cluster keys, and it'll put all the data close, so you don't have to read and do scans. You just pretty much start reading till you're in with your cluster block. So these are options, and sometimes that can make things very slow if it turns out that you're reading across many cluster keys. So you have to be careful about when you use it, but you should theoretically know your application, know the data, how you've chosen to model it, and know how you're going to pull it and use it. That's another very powerful mechanism to pull data and store data. So, full table scans. Ooh, everyone gets nervous when they see full table scans. Well, full table scans in general obviously are pretty bad. That means you're looking at all data in the table. Odds are you probably don't need all the data in a table. But there are times when it's actually not so bad. And sometimes it's actually better if you actually do a simple calculation of, if you look at the statistics of how many rows I'm pulling from the index, and then how many times I'm pulling from the data, from the table itself. And it turns out, and again, this is not a hard and fast guideline, but if you're reading 5 to 10%, or obviously more, of the actual data, and you want to pull it back, or you're touching that much data and criteria that are not indexed columns of that data, it's almost better just to do the scan of the data of the table itself, particularly if it's clustered. You might end up actually reading fewer blocks than pulling all the index blocks, because remember, index data is also stored somewhere in some disk or in the operating system somewhere. So that's general guideline between 5 and 10% is where that sort of break-even point is. If you're anywhere over 10%, you probably want to force a full scan rather than the indexed path. So that might be an example of a hint that you would put on. You're going to almost always be doing queries that pull tons of data, God forbid. You might want to force a full scan there instead of having the database try to use an index and do more work. Again, small tables, we talked about this a little bit earlier, you can store them as index-only tables, right? So it might be a simple lookup, like the example earlier, where you have a department ID and a department name. And you still have to do lookups, just store that in the index. It's not a lot of space anyway. And then consider how much data you've already got in, and I talked earlier about the database is buffer cache. So when I said earlier you can cache tables in memory, if you know you're just going to be reading the same things and similar things over, force those tables in memory, then you don't really have, it doesn't matter if you're doing scans because you're now scanning through memory, you're not scanning through physical disk. You have to make sure you balance how much memory you allocate for it, because otherwise you're going to end up paging. And then your operation now becomes twice as expensive because the data you're going through that's in memory that turns out to be paged is not going to be stored nearly as efficiently as if you lay the data out in tables in sort of I can do it and plan it ahead, as opposed to things that are paged just because whatever paging algorithm your operating system has. So full table scans, sort of scary, but not so scary. Not necessarily bad. We're halfway through, so that's about fine. So, well, we started like that.
Okay. I'm just saying slice-wise. We're halfway through.
Actually, we're up to 50, so
Oh,
I split all those last time. And the harder ones are coming up ahead. So, subqueries. This is where you're gonna typically spend most of your time. So when you have subqueries that you're typically gonna find SQL statements that do sorts and do filters and they do in loops. So a subquery is where you have a SQL statement that has a parent and you're using like a exists, not exists, in, not in type of clause. Those are called subqueries. And you have two different types. You have non-correlated and correlated. So a non-correlated means not connected. If you have a subquery which doesn't bind to the parent query, you want to be careful about that because while it only gets executed once, sometimes you may end up doing loops and loops of your data. And I'll have lots of examples. We'll talk about this. You have correlated subqueries, and these typically get executed once for each record in the outer query. So you might end up again, doing a loop and another nested loop of data. So in general, correlated, non-correlated subqueries you want to be very careful about. Because you're going to be doing the loops, you're going to do filters, you're going to be doing sorts, or you may actually not need to do that. So we're going to spend a lot of time actually going through a bunch of examples of SQL statements that we can rewrite in order to produce better plans. So this slide is kind of dense. I'm sorry, but I'll give you a few seconds to memorize it. Okay, everyone memorizing?
Done.
Well, I guess you have cameras theoretically, you can take pictures. So these are sort of general best practices that you want to use when you find nested loops and filters based on subqueries, correlated or non-correlated statements. You want to be very careful to make sure you use, regular joins. You don't want to use nots as much as possible. You have to be careful when you have where not exists because you're maybe generating a filter. Sometimes it's a good thing to do, sometimes it's not a good thing to do. Wherever you have where, some column in, some subquery, you may want to replace that statement with a hash or some sort of sort merge. And I'll give specific examples of this if the columns are not column. You want to be very careful using not in. Not in is almost always one of the most expensive operations you can do. So there are usually better ways, and I'll talk about different ways to go. If you have to keep it as a not in, and again, I'd be surprised if you couldn't find a way to rewrite it, you can use a hint to say unnest the data or merge with an anti-join hint in order to force the Oracle Optimizer to rewrite the statement, to rewrite the plan, to come at it for better. So again, remember it's got that SQL wizard facility to be able to help rewrite plans. Well, it's smart enough to say, all right, Leo didn't know what he was doing. He was just typing really fast, and therefore I'm going to rewrite the statement for him. So sometimes the optimizer will actually do that on your behalf, but you can't count on it. So maybe you just force it to unnest the statement. If you remove the correlation where you have some column equals and some subquery, you can avoid doing filters potentially if you don't correlate them. And anytime you find something where not column or not equals column or greater than or less than or any of these range type scan devices, it's going to do a filter on a range scan, so you're going to want to try to rewrite it. So now let's look at actually rewriting some statements. Everyone got this one memorized? It's going to be a quiz later. One second. Did I skip this one? No. Is this the next one? Yes. Okay. So this is an example of a non-correlated subquery. I'm selecting employee name from employee, or employee ID, I'm using an in clause, and I just have select employee ID for sales, where sales is something in sales pro. So this is non-correlated. In other words, I'm not joining the criteria in sales with the criteria in employee. So I'm actually going to, for each record in the employee, do this query. I'm going to execute this once, produce a big list, and then try to filter it out. So I could rewrite this by simply doing a join from the two tables, where employee ID is employee ID, sales, and sales. And this would be much, much faster. Particularly if I know the IDs to produce lists. Another alternative way to write, again, you can write this many, many ways, is I could select employee name from employee where exists, and now I'm doing a correlated thing where I'm selecting, basically, I'm matching up by the employee ID, I'm putting my sales criteria, and that's actually the correlated query. So if it finds one record here, then it stops. So it basically loops through all these and tries to find a match. The difference between exists and in is that exists, if you think about it, it's very existential. is it there, is it not there, is something there? And so it stops when it finds the first item. Or if it's where it not exists, it'll stop, you know, again, where it does or doesn't find an item. Whereas in says, hey, am I in that whole list? It has to collect the entire group and execute the entire statement in order to populate it. So in general, you want to be careful. If you're just trying to sort of check if something exists, don't necessarily use in, particularly if you're not trying to pull any fields. This example is a very expensive query. Select employee name from employee where employee ID not in, you know, select employee ID from sales. That's, you just don't want to do that at all, because now you're doing loops and loops. If you think about how you would actually execute that, if you became the optimizer and you figured out how you got the data, you would be doing a loop over a loop. So maybe you can rewrite it this way, select where, I'm going to use a not exist. You have to use not in, better to use not exist, because anytime it finds one, for each item in here, it'll just stop. So if you get lucky, maybe it'll find a bunch very quickly, and it'll stop very quickly, as opposed to having to generate the entire collective set. Again, that's a small subset of possible queries. Another operation called is the minus. So the minus, if you think about it, it's sort of the opposite of union. It's basically, instead of union, where you collect the data from two different SQL statements and combine the two record sets, minus basically compares two record sets and removes. So if you think about it, if I'm doing a minus and I'm pulling all the data from employees minus the ones who might be stockholders, I obviously have to generate, you know, a sort. I have to sort both of them. I have to filter. In this case, I'm doing 2 full table scans because I'm pulling all the data from each of the tables. So that just happens to be the way it is. That's not too bad. But I'm doing a massive sort in order to, you know, compare the data at the end of the day. So I can use it to use some sort of nested index scans. So I might select, you know, data from the employee where it doesn't exist, the data from the stockholder. So instead of doing 2 scans, I'm doing a scan over this, and here I'm actually doing a query, where the query is actually going to be able to use the index. So not only have I eliminated the sort, which is good, that's a potentially expensive sort if I have lots of employees. Hopefully the company will grow and have lots of employees, and lots of stockholders. But here I've eliminated 1 table scan and I've eliminated this sort, right? Or again, using a hint, you can tell it to use an anti-join. And I would select, you know, birth date, last name, first name for employee, where all this stuff not in. So I'm using it in, but I'm forcing it to use an anti-join to connect the two. And generally, this is going to be the fastest. This is a potentially okay alternative if your stockholder table is fairly small compared to the size of your employee table. And again, that would be something you would know and you would play with because you would hopefully understand the data you have in your application itself. So be careful about minuses. You don't want to.
I have a question.
Yes, please ask.
So, it's a really good example about the size of the company. So today, the company has
20 employees,
10,000
15 of whom are
employees and
stockholders.
5,000 are stockholders.
Correct.
And you're implementing this application and you ran all the profilers and you figured out that this is taking a lot more time. So you went and you got your minus down to,
The second option,
And that's
let's just say. Yeah.
so, you know, a year later or 2 years later, the data profile changes.
Absolutely.
So at that time, is there any way to dynamically handle these changes?
Yeah, so there are two approaches. Number one is, the first guideline is do tuning more than just once. Try to do tuning once a year to find, so you'll find which ones are painful. That will help you identify which is
I mean,
painful, and I think
that's
you
when you
understand
own the application, right? I mean,
that. Yeah, I mean, if you're an IT guy, I mean, hopefully you do. But more to your question. So, if you're saying that, basically the question is, maybe today this is the best plan, but it turns out the way the data might look 6 months from now or a year from now, this might be the best plan, or vice versa.
Mhm.
How do you force it to do one thing or another? One thing you can do, and this again, you have to have your database admin, is recollect statistics on those tables. So maybe every 6 months or every year, you run analyze on the tables, and it will know the distribution of data that might exist in the 2 tables. If you know that you have no ability to change the SQL, because you can't force your SQL to do one thing, Then you basically have to say, all right, I think the distribution of data will look like this, and I think the long-term, you have to do your best guess, and pick which one, maybe today is 10% slower, this one is 10% slower compared to this today. But if the data distribution turns out to be something very different from what I expect, which of course always happens, then in the worst case, if the distribution changes, this will be faster long-term. So I'll pay the 10% price now, particularly if it's slow, this data is small, and this statement is not too expensive or whatever. And then you just have to say, all right, I'm just gonna do that. So again, it's a guessing game, you're right, it's a challenge.
All right,
To do it.
follow-up question.
Yes.
Have you ever seen people in an application layer, try to accommodate for this? Basically, so those the analysis,
Yeah.
all of that can be put in the
It's stored in the
layer.
data, it's stored in the data, yeah.
And then you could actually have a time procedure that runs every half a year, that produces something for the application layer can check for it and say, okay, I'm gonna use this or use that to get the same amount, the same data set. I mean, that'll be kind of a
Yeah, I
software
mean-
application. Has that been done?
I'm sure it's probably theoretically been done. I mean, depending on the kind of so it's very common to have an application where, you know, and I've been through many of these, and even Selectica to some degree has it, where you've got a very sort of flexible data model. And you define your application with some sort of data modeling tool, which you describe a logical application. And your engine, in this case the selecting engine we'll use, reads that data model and actually figures out, based on the relationships and the criteria in the model, what is the underlying SQL I want to use to pull data, push data, do, you know, run a report, run a query. So what, and this existed in a prior company that I worked at, we had some guy who was like super genius on SQL, orders of magnitude more than me. And basically, what we did was we tuned the engine that read these data models and translated them into SQL. So we understood that we, again, sort of kept our own sort of statistics, you know, at the application layer, the ones that we thought were useful. And as we discovered that constructing SQL statement this way is more efficient, we would actually put that in our data engine. And so as we're translating the model into physical SQL statements for reads, writes, get whatever they might be, we would translate it into whatever was most optimal. So our developers didn't actually write the SQL. What they did was they did the modeling, and you had a few very smart database people who knew how to translate the model most efficiently for whatever functions the model, whatever criteria you could put in the model, whatever constraints you could put in the model, how best to translate that into Oracle SQL or into DB2 SQL or into SQL Server SQL or into MySQL or, you know, whatever underlying engine. So that's typically how it's done. But that's a good question. Yeah, your data, but the most important point I think that Leah brought up was that your data distribution will change. So what might be optimally good 3 weeks after you go live may be very different. Hopefully not too different, hopefully you've thought and kind of project this, but maybe very different a year down the road for different customers. Or maybe different for one kind of customer, their data looks like one thing. They have lots of very light users who don't do things, but there are lots of users, you know. And then you may have other applications where you have very few users and they do so much. And so you maybe have to, you know, slice and dice your how you store the data and how you try to access the data. And so that's important to think about. Again, it all comes down to knowing your application, trying it again, kind of just learning and looking again. But yeah, that's a very good point.
One more.
Okay, you get 3, so you have 1 user. It's like timeout.
So the net
Yeah.
gain from all of these optimizations.
Could be,
You're producing a product. The product is sold to 2 types of customers. One, small customers, you know, mom and pop shops that have,
right.
I don't know, 1,000 rows total with older tables, whatever.
This is all moved.
The second one is huge Chevron type customers that have millions and millions and millions of rows of data.
Correct.
Would you, as an application producer, as an application developer, as a manager of software business,
Right.
come out with 2 lines of software, one that has queries optimized